goes to the review of the next week's course.
That is a little bit too hard. Sorry for that.
Okay. So last course you asked me about the use of homeomorphism. I did that as well, but homeomorphism can be used in an elegant proof of broad fixed point theorem because any f that is a homeomorphism preserves the fixed point property. So you can use this to prove the broad point theorem, and maybe we can talk in the last course.
I think when you think of like homeomorphism, you're thinking about like two similar topological spaces or two spaces have like similar topological properties. So maybe you can think about like when two people are facing two different like consumer problems and found that okay, so they have like maybe 2 or 3 commodities to consume. With the homomorphism, we can just move one to the another. It's just the same property because they have similar topological properties. So you don't need to like to solve for apple for one and for banana for another one. Just move everything toward there and just use the homomorphism argument. You can solve a bunch of similar problems with similar topological property at once.
Okay. So let's start at the last theorem in the last course state. It states that for a function from x mapped to y, f is continuous if and only for every open set u in y, the preimage of u is open. Okay, let's prove the right hand side. So how can we use continuity to prove such property? First, draw some diagram. I think that's big enough. Okay, so for every open set U, in Y, suppose its preimage here, maybe here. Is preimage. We need to prove that this is open. Okay, so to prove this set is open, we first pick a point here. That it is X. Then its image is here, Fx. We need to prove that there is some neighborhood such that it is contained in the preimage of U. So we're using continuity because we can open some, for any epsilon ball, we open here. We can find a delta ball. Such that the image of the delta ball will lie in the delta ball. So the delta ball will in the preimage of U. Hence, the preimage of U is open. Okay, let's write down. So since U is open for any point X, there is this epsilon larger than 0 such that the neighborhood of Fx is in U. since f is continuous, there exists a delta larger than 0, such as that when P lies in the neighborhood delta ball of X, the image is in the epsilon ball. In the epsilon ball. Hence, the delta ball is in the preimage of the open set U. Oh no, epsilon ball. Which is a subset of preimage of U. So the preimage of U is open. Okay, that's the first direction. For another direction, we need to prove if this property holds, then f is continuous. So to prove f is continuous, we need to prove f is continuous at each point. So suppose there's a point x here, and the image fx is here. We need to prove that for every epsilon ball here, there is a delta ball here that its image falls in the epsilon ball. So by the property, the preimage of the epsilon ball is open, maybe like this. The preimage of epsilon ball. So by the property, this is open. So we can open some neighborhood here, which is a delta ball. So we can find that this delta ball's image falls in the epsilon ball. So f is continuous. Okay, let's write down. For every epsilon larger than 0, by the assumption image of the epsilon ball is open. Hence, there exists delta larger than 0, such that the neighborhood of the delta ball of X is contained in the preimage of the delta ball, epsilon ball. So this implies that the image of the delta ball falls in the epsilon ball. Okay, so this gives us the continuity. Okay, that's the proof of this theorem. This theorem is quite important because we'll use again and again in the following course, in the following review. Okay, first we have a very similar corollary. It states that f is continuous if and only if for every closed set K in Y, the preimage is closed in X. I just change the open to closed. So to prove this, we can prove this property is equivalent to this property. Okay, so for every open set U in X, the complement of U is closed. So by this property, the preimage is closed. So the complement of the preimage of U complement is closed. It's open. And this implies that the preimage of U is open. Because you have something like this. You just use this property. So we have the closed set property implies the open set property. The converse is exactly the same, just change to closed set in X and complement is open, blah blah blah, and use the same trick. Okay, similar for another direction. There's a very important property of continuous function, that is, a continuous function preserves compactness. So an image of compact set is compact. So if F is continuous, then for compact, any compact set K in X, the image Fk is compact in Y. Again, we can use the previous theorem to prove this. So to prove Fk is compact, to prove a set is compact, we first have to pick an open cover that covers Fk. So we can find some finite cover on it. So let U alpha be an open cover of Fk in Y. Okay, because F is continuous, by the previous theorem, the preimage of the U open set U alpha are open. So the preimage U alpha is an open cover of K. Because U alpha covers Fk, its preimage must cover K as well. Okay, since K is compact, there is this finite cover of K. you say U1 to UN, oh no, the preimage of U1 to UN. So the image of this subcover covers Fk. Of Fk. Hence, Fk is compact. Okay, that's the proof of the theorem. Okay, now we are ready to use the theorem to prove two important theorems. The first one is the homeomorphism theorem. Which states that if F is continuous bijective on a compact set X, then F is a homeomorphism. Recall that a homeomorphism is a function that is continuous bijective and its inverse must be continuous. So we have F is continuous bijective. So this tells us that the inverse of F is continuous. So to prove the inverse of F is continuous, we can use the property of the corollary there. We state that F is continuous if and only for every closed K in Y, the inverse image of K is closed. So the inverse function of inverse F is F. So F inverse is continuous if and only for every closed K in X, Fk is closed in Y. So we can, it's our basis to prove this. So now for every closed set K in X, because X is a compact set, K is a closed set. A closed set in a compact set is compact. So K is compact. Okay. Since F is continuous, continuous preserves compactness. So Fk is compact. And compact implies closed, so Fk is closed. So we are done. Just use the combine of the corollary and the theorem. So you know that if your F is continuous bijective, defined on a compact set, the inverse of F exists and is well defined. Okay, there's an easy corollary that the closed interval 0, 1 is not homeomorphic to the real line because the closed interval is compact, well, R1 is not, so they cannot be homeomorphic. Or you can think that because a closed interval is bounded, so where even if how you stretch or bend the closed interval, it must be bounded. You cannot stretch it to infinite long, so they cannot be homeomorphic. Okay, so here comes another important theorem, the Weierstrass theorem. If f is a real value function and f is continuous, x is compact, then f achieves its maximum and minimum. That is a very useful theorem in the graduate microeconomic course. Okay, before we give an example, let's prove it. So since f is continuous and x is compact, since continuity preserves compactness, fx is compact. Compact in R. So by Helm-Brochel, fx is closed and bounded. Bounded implies that the supplement and the inflement exist. And the closeness implies that there exists x and y in x, such that fx equals the supplement, and fy equals the increment. So this proves the Weierstrass theorem. Is it okay so far? Okay. Wait. Okay. If it's fine, I'll give an example to use to show the power of Weierstrass theorem. Okay, suppose in the market, there are n kinds of goods.
x1 to xn with price p1 to pn larger than 0. So we often suppose that every individual maximize its utility in the market under its budget constraint. Individual maximize its utility under budget constraints. So that is, he solves the max of ux, which is the composition of x1 to xn, such that sum pi xi is smaller than the budget constraint. So if the utility function is continuous, then the maximization point exists. And the best consumption bundle is called the Marshallian demand. This is called the utility maximization problem. So we will use Weierstrass theorem to prove the existence. Okay, first we let A equals the consumption bundle that is feasible. And each consumer must own a goods with non-zero goods, because you can't borrow goods from the market. So each xi larger than 0. Okay, so if we can prove such set, that is the budget constraint is compact, then by the continuity of U and the Weierstrass theorem, we have F achieves its maximum and minimum on A. So we first show that A is bounded. Because A is bounded by the interval 0 p x1 over, y over p1 times to 0 y over pn. So it is necessary for us to assume that pi is larger than 0. So every price cannot be 0. Okay. Next, A is closed. Notice that this is a continuous function. The sum pi xi is continuous. let it be f. So the inverse image of the closed interval 0y, because it must larger than 0 as well, is compact. Oh no. Is compact. It is closed by the erased corollary, since f is continuous. The inverse image of closed interval is closed. So A is closed. Hence by Hell, A is compact. That's by Weierstrass theorem. You achieves its maximum. Okay, that's the proof of the existence of the utility maximization problem. So for example, if you want to prove the first welfare theorem, which states that in a competitive equilibrium, the outcome is Pareto efficient. Before you prove the theorem, you always need to make some assumption like this, that every individual maximizes its utility under its budget constraint. So there is the Marshallian demand. But before you keep going on, you first have to prove the existence. So the following you do to prove the theorem is make sense. Otherwise, if it does not exist, then you can't do anything. So the compactness assumption is very critical, because a continuous utility on a compact set means that we can find the maximization point and minimum point. And with some another assumption, we can even show that such demand is unique. Any questions? Well, if there's no any questions, I think this the ends of the preview.